Hey guys, and welcome back to the channel. As you can see, I am back in the US, back in Chicago, and it seems my travels have caused me a bad case of ligma. My throat is hurting a bit at the moment. So I'm going to try and get through this video decently fast. And yeah, let's go ahead and talk about how we would calculate the number of unique active users on a site at a given time. Okay, so today we're going to be calculating the number of unique users on a site between a given time range. So for example, if I have my OnlyFans site over here, very real in fact, and I have the following list of things that I'm willing to sell, one question that I might have that I want to ask OnlyFans is how many different unique users viewed this content between last week and this week. I might be making a ton of money, but if it's just one or two of you guys that's buying everything, that's not looking good for the future. It would be better if I had plenty of different people looking at my page. Cool. So let's actually formalize some problem requirements here. So number one is that we want to be able to calculate the number of active users on a site. So that could be for just a given instant or also just any possible time range, which is going to make this a bit more complex. Number two is that a user can be online on multiple devices at the same time or have multiple different sessions at the same time. Cool, and then I'm not going to go too crazy into the capacity estimates. We'll touch upon those a little bit later in the video. But the gist is we can have billions of sessions active at one time on a variety of different devices. Cool. So the first thing that I want to touch upon is just some terminology or a paradigm overview that I'm going to use for basically building out the foundation of this video. So the idea that I want to describe is the concept of a session, where when a user logs in on a given device, that device login is assigned a particular session, and when they're no longer active on that device, we should keep track of the fact that that session is no longer active. It has been completed. So the way that we're going to at least attempt to assign all of these sessions is via something that I will dub the session service. So the session service is going to do the following. When I log in, it's just going to assign me some sort of ID for the session. It doesn't really matter if this is a UUID, it doesn't matter if it's a monotonically increasing sequence number. What's important to me really is just that that session number is going to be unique per user, so that when I'm looking eventually per user, I can actually just go ahead and quickly confirm that this is, a new session and not a previous one. Cool. So the way that we can pretty easily do that is, let's say our session service is partitioned, and we have a sessions database, which is also partitioned by user ID. Basically, when I first log in, the session service can reach out to the database. The database will assign me a new session ID based on the primary key, and then we can go ahead and just use that for the duration of this session. Cool. And then, so what would that look like? Well, I've drawn out a small diagram down here. We've got some load balancer. The load balancer is going to assign me to a session service based on my user ID. We can just use consistent hashing. And then similarly, again, we have another load balancer between the session service and the actual sessions database, because this is going to be a pretty big table if every session ever is going to be in there. So we're going to need a lot of partitions, and we can just do that based, again, on user ID, or rather the hash of the user ID. Cool. So what would that table actually look like? Well, we would have our user field, our session ID field, the start time and the end time of the session. And I'm assuming that if there is no end time of a session, that means the session is still going to be in progress. So the nice thing we can do here is also just index by session ID, so that way we can quickly query all of the sessions through all time, and they're going to be ordered by start time effectively. Cool. The next thing we want to talk about is session expiration. So we just described how when I log in, I can be assigned a new session for my device, but now we also have to talk about, well, if I haven't been doing anything or the server hasn't detected any activity from me, it has to consider me logged out, because I'm not always explicitly going to log out. Sometimes I'll just close my browser or close my computer, and then we're not going to hear from me anymore. So the main idea is basically that every once in a while I should probably be sending some sort of heartbeat to the session server indicating that I'm logged in or that I'm active. And then the gist from here is that the session server can effectively just keep track of which heartbeats it's received, order those by the received timestamp that it got them, and then run a background process saying, ooh, here are all of the session IDs that I haven't received heartbeats for within a certain amount of time. That means I should probably go ahead and consider them expired. Let me go ahead and write the end time to the database indicating that that session has been completed. Cool. So the data structure that we can use here is one that we've seen plenty in the past. We can use something like a doubly linked list with a hash map so that we can quickly go ahead and order and basically remove the session IDs as we receive the new heartbeat, and then put them at the end of the doubly linked list. So this is going to make all of our accesses and moves throughout that doubly linked list O of 1, and yeah, should keep things relatively efficient. So again, that background process is just going to expire the sessions that we don't see heartbeats for. So for example, if I have a user 11, a session 4, and that's pinging our server every 10 seconds, and user 12 with session 9 decides to stop pinging, maybe after 30 seconds, the session server is going to say, ooh, I don't see that anymore. Let me go ahead and put the current time as the end time for that session. So the next thing that we're going to do is very typical Jordan behavior, which is obviously I'm going to take all of the changes going to that sessions database and use that as change data capture. The reason being that I want to consume it downstream and build derived data off of it. So from our session database partition over here, we can basically take the changes on every single given partition, put that into a partition on Kafka, effectively meaning that Kafka is also going to be sharded on our user ID, and then finally throw that into Flink, again meaning that it would effectively be sharded on user ID. And then from Flink we can create all sorts of derived data and insights that we wouldn't have been able to do otherwise by virtue of being able to run custom code. Again, of course, I always end up using Flink because I know that state is getting checkpointed, so I don't really have to worry about dealing with the fault tolerance as much here. And yeah, just the fact that everything in Kafka is durable means that I'm really not worried too much about things going down. So the question now becomes, well, if I'm going to use Flink to maintain some state and then ultimately create derived data from our sessions database, what derived data do I want to be creating? And so before I can go ahead and make any claims there, first I would like to show off a few different ways that we can actually go ahead and calculate the number of unique active users. So the first way that I'm going to demonstrate is what I would call the naive calculation. So let's say that we want to find the number of unique users that we've seen active at any time between 108 and 123. So this is our start and our end time right here. So we're basically going to have to do 3 different checks and then combine them all into one set. So the first thing that we need to do is find any sessions that basically started after 108 or started before 123, meaning that, you know, this would be a good example right there, because then we're going to be active during that window. Another option for a session that we would include is one that started before 108, but actually the end time is between 108 and 123. So that's option 2. And then option 3, which is also possible, is, ooh, we start all the way back here, and then we end after 123 as well. So if you think about it, this is actually going to be a little bit complex. The first 2 cases that we just mentioned are relatively easy to solve with indexes, right? If I order every single session that I have by their start time, and then I create a second index ordering every single session that I have by their end time, I can easily binary search through just checking for the range that I care about. That being said, if I have a criteria that is both filtering on the start time as well as the end time, one single index on either the start time or the end time field is not going to be good enough for us. It's actually the same problem that we see when we try to query by geolocation data. Effectively, I can very easily find all start times before 108, but there's no good filtering method for me to combine that with all end times after 123, which is not so easy. In theory, we could combine both indexes and do a join, but that could potentially make for a gigantic join, and that could be very inefficient. One option that you may be thinking about here, if you are thinking about the 2-dimensional index problem, would be that we could, in theory, use something like a multi-dimensional or almost like a geolocation index here. But personally, I think that becomes a bit overkill, and I'll talk a little bit more about how I want to solve this problem otherwise. Cool. So now the next thing that we're going to be talking about is calculating the unique number of active users a little bit better so that we don't have to scan over a ton of data and consider all of these different sessions. So let's imagine that we had snapshots of active sessions at a bunch of discrete points of time, right? So let's say in this example that I'm going to do below, we take one every 5 minutes. So now from these discrete snapshots, we may actually be able to figure out all of the sessions that were active during a given time range. And then of course from all of the sessions, we just take all of the distinct user IDs. So let's say at 105, we've got the following snapshot, user 12 has session A, user 12 on a different device also has session B, and then user 13 also has session A. Now we see all of our session snapshots listed out below. Cool. And basically all we would really do is take the union of all of the users across all of those snapshots with a couple of small edge cases. So the first is that for a guy like this, 13A for example, we can see that 13A is no longer around in the 110 snapshot, meaning we actually have to go ahead and check the exact start and end time of user 13 session A. so that we make sure that it actually ended after 108 and not before 108, ending at 107, because then we wouldn't want to count it. And we would have to do the same thing with this guy over here, 14C. We can see that it was existent at 125, but does that mean that it started before 123 or after 123? It's hard to say. We would have to actually go ahead and cross-reference with our sessions database, which actually has that information available. So then we're going to merge all of the user IDs into one single set. And this is going to be quite a bit more efficient because now we're actually just reading from a limited set of snapshots as opposed to having to do a potential scan over all possible session IDs of all time, which if you think about it, you're basically looking at every single user session on your website, which has billions of users. That's going to be very inefficient. That being said, this guy still has quite a few problems as well, which we're going to cover in the next slide. So there are two main problems, basically. The first is this. If we're reading from many session snapshots, keep in mind each session snapshot could be pretty big, right? We're talking about potentially billions of active sessions in a given moment. We're going to be reading lots of duplicate data, and that is going to be bad. So for example, user 12 was active on session B at both 105, 110, 115, and 120. And so now we're reading that data 4 different times. We only wanted to read it once, so this is going to be a bit overkill. And more importantly, the previous solution isn't actually correct. So why is that? Well, if we're only taking snapshots every 5 minutes, what if a user was active right here in between 2 snapshots? Then we're never even going to get word that their session existed in the first place, and we're never going to see them, and now we're going to undercount. So that's going to be a problem too. So what can we actually do both to ensure ideally better performance, but also most importantly, correctness? Well, we're going to need to take some sort of hybrid approach between both our snapshotting solution as well as our actual linear scan solution. So here's the way that I've come up with that I think would do this in the kind of perfect, accurate solution way, which is, let's imagine we have our snapshots still every 5 minutes, and right now we're only going to care about the snapshots that are just outside of the time range that we care about, because we want to make sure we incorporate every possible solution. So in this case, we've got one at 105, which is the first snapshot before 108, and we've got one at 125, which is the first snapshot after 123. So the first thing that we're going to do is we're going to get all of our sessions with a start time between 105 and 125. We know how to do that. If we have a database index on all of our sessions, we can easily do this calculation. It's just a range query. Same thing with all of our ends. Note that we're doing 105 to 125. The reason being that someone could be active from 106 to 124, and that wouldn't be reflected in our snapshot data over here. So we actually have to query the entire range between our 2 snapshots, and then once we consider all of those potential sessions, then we can actually use our snapshots themselves. So now we're going to go ahead and take a look at all of our active sessions at 105, for example. We've got user 12 active on session A and user 13 active on session B. Now, even though we know that these guys were active at 105, we now have to ask ourselves, ooh, was this session still going at 108? And the only way that we can actually determine that is by figuring out their start and end times and probably going back to our session database to go ahead and do that cross-referencing. The other thing is that basically, for all of our sessions that are intersecting from 108 to 123, so basically that's going to be all the valid sessions from here, all the valid sessions from here, all the valid sessions from here, and all the valid sessions from here. Now we basically have to go ahead and keep all of the user IDs that we saw that were distinct, count them up, and return that to the user. So cool. That is actually how we would go ahead and do this. What would this look like from implementation details and the actual technical perspective here? So in order to actually do this, we've now mentioned 3 different types of derived data, right? We need basically one index to index all of our sessions by their start and their end time. It doesn't necessarily have to be a perfect index, but ideally some sort of partition table where the partitions are aligning nicely with the start and end times of the session, and that way we can really quickly find all of the sessions that have a given start time or have a given end time. So that's basically 2 different tables that we need to maintain. We can do this by just using some time series database and partitioning it properly. So that we can easily go ahead and get these sessions. Ideally, or rather unfortunately, there is probably going to be a lot of data, so it's possible that even for a given time range, we're going to need a couple of different partitions, but that's okay. Ultimately, it's going to be a distributed read on an immutable table, and what can you do? Cool. Number two is that we need to be able to find the active sessions based on the discrete timestamp, right? So effectively, these are our session snapshots. So in the above example, it's something like this. At 1:05, which sessions were active? So the way that we can actually go ahead and do this is by using Flink again. So Flink, what it'll do is it'll basically keep track of all the newly created sessions, which it'll get through change data capture, and basically it'll keep those buffered in its own memory. It's all partitioned, so we should be able to do this relatively easily. And then basically, every few minutes, Flink will look at all of the active sessions for which it sees a start time but not an end time, and then basically snapshot those over to a database. Additionally, what it'll do is if the end time does come in for a given session, indicating that that session is completed, Flink will then just remove it from its memory. So in subsequent snapshots, that session won't be present. So hopefully that all makes sense. And then ideally, what we could do is actually publish back to MySQL. That way we can get nice joins on the snapshot data with the actual official start and end time of each session. However, in reality, it's possible that this may end up being too much data. We may have to put these snapshots in something like HDFS via Parquet files. And if we have to end up doing that, what can you do? It'll be slow, but such is life. Cool. So now let's go ahead and talk about some of these problems with snapshotting. Because I've spoken about these snapshots like they're super easy to make. And the truth is they're not that hard to make, but objectively it is a ton of data, right? Because at the end of the day, if we want to take a snapshot saying at X time which sessions were active, well, we need the user ID and the session ID for every single active session. And this could be like a billion at a time. So keep in mind that the user ID and the session ID alone are probably 16 bytes because each of them is probably 8 bytes if we want to represent them with a long. And then from there, let's imagine we have a billion active sessions at a time. This means each snapshot itself is a whole 16 gigabytes of data. Now the problem with that is that let's say we're taking one of these snapshots a minute, that means every single hour we're publishing a terabyte of data, and if we're publishing a terabyte per hour, that means we're basically publishing 9 to 10 petabytes of data per year. Now look, realistically, if you're Google, if you're Microsoft, if you're Amazon, you can probably afford that and it's not a huge deal. But depending on how many services you're actually doing it for, maybe you do want to save those storage costs or just in general the actual cost of buffering everything in memory, because that can be kind of expensive too. Like keep in mind that we do have all of these different Flink nodes to take the snapshots, and that's not necessarily an easy thing to do. It means we're going to be using a lot of RAM to actually buffer all of these different sessions. So even though we can handle this, if we want to make things cheaper and potentially faster, a lot of companies have opted to begin using approximation methods here to actually do this in a little bit of a better way. So we'll discuss that in a second. So if you've watched my 1.0 series, you'll probably imagine that I am talking about the hyperlog log. So the hyperlog log is a probabilistic data structure that allows us to compute the cardinality, which basically just means the number of distinct elements within a set. And the whole point here is ideally we want to be doing this with relatively low memory usage so that we can stick this on any given server and easily compute the cardinality of all of our given active users in a given moment. Cool. So how does this actually work? Well, let's imagine I take a given user ID and I represent it in binary. So you can see I have 32 bits here. So the first thing that we're going to do is do the following. We're going to assign the first few bits for something called bucketing, which means we're going to bucket all of these user IDs into different buckets based on what those first few bits are. And then the other thing we care about are the number of leading zeros at the end of the number. So in this case, we've got 5 at the end of our user ID. Cool. So the way hyperlog is going to work is as follows. Let's say we have 100 different user IDs that have come in that are potentially active at the moment. Basically, the first thing that we're going to do is bucket each one into multiple different buckets based on those bucketing bits. The next thing that we're going to do is find the user ID in each bucket with the maximum number of leading zeros. So in this case, it's 5 for this user ID, but maybe in a given bucket, there might be 7 leading zeros for one user ID. What we're then going to do is each bucket is going to take that user ID with the maximum number of leading zeros. So maybe bucket 1 has 3, bucket 2 has 5. We're going to average those numbers together, right? So 3 and 5, the average would be 4. So that we're going to call that X. And then the cardinality of the entire set is going to be 2 to the X. So in this case, 2 to the 4, which is 16. So let me make this a little bit more concrete. Basically, let's say we've got the following buckets, right? We've got our user IDs from both buckets. If I look for the user ID with the maximum number of leading zeros, in bucket 1, it's going to be this guy here with 3 leading zeros. bucket 2, it's this guy here with 5 leading zeros. We're going to average those together, take 2 to that power, and that's going to estimate that there are 16 elements in this set. Now clearly, as you can see, there are only going to be 8 elements in this set. It's a probabilistic data structure. But the more buckets that you have, the better estimates this guy is going to create, and ultimately that's going to be a nice thing. Now I'm not going to go too deep into any of the mathematical guarantees about this probabilistic data structure, because frankly I think for us software engineers it doesn't really matter as much, as long as you understand the general idea, which is basically saying, ooh, you know, if I've seen enough user IDs that one of them has 5 leading zeros, well, there's a good shot that there were probably around 32 of them, because, you know, then my expected value of, you know, seeing such a user ID is checking out. So again, if you care more about the mathematical stuff here, go look up hyperlog on Wikipedia. There's plenty you can read about it. But yeah, hopefully the intuition makes a little bit of sense here. So the question now becomes, well, how do we want to build our hyperlog logs? The idea here is, you know, every certain time granularity or time period, we want to be taking another one of these hyperlog logs. The reason being that you actually can't remove elements from these hyperlog logs. The idea is just that, you know, within each bucket, we're not actually storing all of these user IDs. What we're just storing is the number of leading zeros, the biggest number. And so in this case, we would just be storing bucket 1 is 3, bucket 2 is 5. If we stored all of the user IDs, then we could actually go ahead and remove elements, but we don't want to do that because the whole point is to use as little space as possible. Great. So, like I mentioned, you can't really remove elements from a hyperlog log. So every time our interval begins again, every time, say, our minute passes and we want to get a new snapshot, what we need to do is just completely clear out our old hyperlog log and build it up from scratch. So the question now becomes, well, if we want one snapshot per minute, and we have to clear out our hyperlog log, how do we actually know which user IDs become active again? Because the user ID is already logged in. Like, it's not going to our hyperlog log and saying, hey, add me back again, add me back. So instead, what we could do is actually do this on our session server itself. The reason being that our session server is actually receiving pings from every user. So based on receiving a ping, we can then add that user ID back to our hyperlog log, which is going to be pretty nice. We can do all of that bucketing on each session server partition. And then let's say our minute passes, we want to take a snapshot. We would go compute that average over all of the buckets, throw that in a hyperlog log database, and then, you know, across all of the session server partitions, we could also take that average there if we wanted to. So for example, you know, in reality, I would have session server 1 and session server 2, and they would both be exporting here. And then when we read back, eventually we can just perform that average. Let's say there are 10 session servers overall, or even 100 of them. You're just averaging 100 numbers. That's not an expensive computation for a database. Cool. So the next thing is just actually going ahead and reading our hyperlog logs from all of these snapshots. I'm just going to quickly demonstrate how we might perform an approximation. In reality, it's probably a bit more nuanced than this, but again, I just don't want to go into the math too much, not only because I'm incapable of it, but also I think it's out of scope for a video like this. So let's imagine, again, we care about all of the number of unique active users from 108 to 123. And we have all of these hyperlog log sketches. So, you know, there's 3 zeros for the 105, there's 4 zeros for the 110, 5 zeros for the 115, 3 zeros again at 120, and 5 zeros at 125. This is 5 different sketches, so we take the average across all of them, take the sum, note that this sums out to 4 leading zeros out of our biggest user ID, and so we're going to now estimate that there were 16 users in this time. So basically, we're just going to be merging our hyperlog logs together from all the different intervals and taking our best guess. Of course, this is an approximation, but we don't care. As long as it's approximate enough and accurate enough, then this should suffice, and it's also just going to be a lot cheaper because now we don't have to buffer all of these user IDs in memory on a bunch of different Flink nodes. Cool. So I'm going to now put this all together in one single diagram, ideally, and that is going to look like the following. If we have our user over here, when the user logs on, they're going to reach out to a load balancer, which based on their user ID is going to connect them to a given session service. From the session service, we are now going to reach out to a session database, which is just an easy MySQL table. This is not going to be written to that much that I think MySQL is going to suffice completely fine. And we can shard this guy on user ID using primary key constraints to ensure that our session ID is not one that we've used before for that user. Is it possible that a user could create 1,000 sessions in like a minute and we could overload MySQL? Maybe, but if they are, they're probably malicious, and I wouldn't mind if their query was slow anyway. This is what we have things like rate limiters for. We should just stop them from creating that many sessions that fast. So yeah, I do think it's fine to have one user ID per shard ultimately, or not one user ID per shard, but basically every single user belongs to just one shard. So yeah, we assign them that session ID, and then from there, all of that data from the MySQL table is flowing through Kafka via change data capture. Keep in mind the session service is also responsible for expiring sessions. So if for whatever reason I stop pinging my session service, the session service will then reach back out to the session database saying, hey, this thing has gone ahead and ended. And again, that is now going to flow back through Kafka as well and into our Flink nodes. So in Flink, assuming we're not doing the hyperlog approach and we're just doing our perfect solution where we have all these snapshots and we're trying to basically export them at a given interval, what Flink is going to be doing is the following. It's going to say something like, okay, for user 12, session A, this guy is currently open and I have yet to see an end time from MySQL. If an end time comes in indicating the session is done, I just delete this from memory. And so now let's say I have 13B available and user 14 with session C. Let's say that minute comes along and it's time for me to snapshot. I'm going to take this entire set and I'm just going to throw it right back in the database. So that's going to go right back over here to the session database. Ideally it can fit because this is just going to be limited basically by the number of users that are actually on that partition of the database itself. But if it doesn't, again, just throw it in Hadoop and we'll have to deal with it later. So yeah, put this guy back in the session database in some different table, maybe call it the session snapshot table, and then that way we can quickly join that with the actual session database to get the start and end times of all of these sessions, because otherwise we would have to denormalize our data, and that's going to be pretty tough. Cool, so that's one thing that we're going to do is publishing these active session snapshots for a given timestamp. The other thing that we're going to do is be syncing all of this data over to the session start time index and the session end time index. So as we mentioned in terms of how we want to get our exact solution, it's pretty imperative that we can quickly figure out, if I have a given timestamp, I can quickly figure out all of the sessions that started within those two timestamps and all of the sessions that ended within those two timestamps. And the way that we can most easily do that is just by building a global index over the session start timestamp and the session end timestamp. And we'll probably need a lot of partitions here because there are a lot of sessions. But as long as we're pretty smart about doing that and make them granular enough, I think this should work out pretty nicely. Cool. And then the last aspect of this whole problem is going to be the actual publishing of the hyperlog logs. So again, we're just going to be doing that from our session services. Each partition, or basically every horizontally scaled instance of our session service, is responsible for a few different user IDs or a range of user IDs based on the hash of them. And we can go ahead and compute the HLL locally on each one of those, and then publishing that number per session service on an interval to the hyperlog snapshot database. I think this is another thing that would also be fine as a time series database, but again, there's not that much data. Use whatever database you please. And then the final piece of the puzzle is just going to actually be reading the metrics. So for the active user service, if we want just an approximate calculation, all we have to do is read from the hyperlog snapshot database accordingly, as I showed in this slide over here. That being said, if we want an exact count, and we don't really care how long it takes us to get it, what we probably want to do is read from both the session start index, the session end index, and then also our session snapshots, which could either be in HDFS or in MySQL. But ultimately, we're going to have to join those with the MySQL data to figure out the exact start and end time of all of the sessions in the session snapshot. Okay, guys, I hope this one made a little bit of sense. My voice is only hurting me a little bit, so that's a positive. But yeah, I'm going to go ahead and get myself to the gym, and I will see you in the next one.